All right, code generation. So here's a Python program. I don't know if you can read it, but what it's doing is implementing select sum of a plus 1 from a table. So the table is just this kind of row class or struct in Python from values 1 to 10 million. And this is kind of implemented in the push-based query execution model. Here's the same program using kind of analogous paradigms in C++. And these slides are available online. I'll send a copy to Andy as well, so you can scrutinize the crap out of these programs if you'd like. If you go and run them, here are the numbers. So it turns out that you get a 37x difference in execution. And even if you account for compile time of the C++ program, it's 1.37 times faster to use C++ than it is to use Python. Now, this is not exactly the same ratios that you have with a database. The big difference is that even interpreted implementations of a database can make static assumptions about types, whereas Python can't. But this gives you an idea of kind of some of the benefits of code generation over an interpreted execution model.
C++ code is bad too, because if you're running time, you grab a clock here.
This is not good C++ code. Okay. This C++ code is meant to be like simple C++ that uses as much dynamic allocation as this Python code on the surface. Yeah. So what does code generation give you? There are kind of two big categories that people look at. Most people, when they think about code generation, think about expression execution. So I have some tree of expressions which I'm executing over and over again. Let me compile this into a chunk of code which executes this expression, maybe over a single value or maybe over a batch of values. The thing that people think about less but actually matters a lot too is inline scans. So you can avoid this batching altogether, and batching kind of introduces its own overhead by inlining scans and basically taking batched computations in a tree and pushing them onto the inside of a for loop. So that's an inline scan. Now, one of the things that really matters, I know Andy covered this a little bit in the code generation slide, is you need a powerful plan cache. And I would argue even with fast code generation, you need a powerful plan cache. The reason is that plan caches basically let you trade off between dynamic and static overhead. So how strict your plan cache is kind of is a function of how and where you want to draw the line between dynamic and static overhead. And this really, really matters in OLTP workloads versus kind of ad hoc data exploration workloads. So here's an example of two queries which map to the same plan. So in MemSQL, basically what we do is we parameterize out values in kind of some common patterns which we'll look at. So here we convert an integer value into an @ sign. And this string is what's called a plan cache key. So when we receive a query, we parameterize it, convert it into a parameterized string, and basically look up this parameterized string in a hash table. Here's a slightly more complex example. So a naive parameterizer would actually parameterize each of these integers to be kind of an in list with 5 @ signs. But in MemSQL, we actually recognize that in lists are a special case and parameterize them like this. So we normalize against the size of an in list. And that's because the size of an in list tends to vary with kind of query by query demands of a workload. Here's an example which you can't really parameterize well. So this is a kind of canonical drill down query, where here we're breaking down sales by region. And you want to kind of double click on some dimension and maybe freeze the region to be the Northeast and look at sales by sales rep. And here, another person wants to freeze the region to be the Northwest and break down by product. And these generate two fundamentally different queries, which, yeah, sure, we can parameterize out the region, but the rest of it might actually have serious implications for how the query is optimized. For example, maybe we have an index on rep, but no index on product. And so these are fundamentally sort of different queries, and they don't parameterize to the same plan. And until recently, this was a big problem in MemSQL, because until recently, code generation was very, very slow in MemSQL. So let's look at some generated code. Here's a very simple query. Select concat of foo and bar. And these are based on the kind of old code generation in MemSQL. So what you'd see is it takes about 0.81 seconds the first time, and this includes code generation, and then obviously the next time you run this very simple query, it's negligible. So a little snippet of code looks like this. So we have some variable for overflow. We set up two what are called varchar temps, just some structs. We have a result value, and then we run this operator called opconcat. This is really easy code to generate. Why is it easy to generate? Well, we make heavy use of templates, and in fact, this thing is templated as well, and does type inference based on, and template instantiation based on the types of all three of these values. So this code basically lets you, as a compiler implementer, separate concerns very easily. So you have the types of your inputs, and you have an operator which handles all kinds of types, which can be implemented separately. And all you need to do is spit out simple code like this. But it's really slow to compile. What's up?
So you have like specialized templates, and then you like basically like smash strings together and compile that, and then I would just automatically link to those specific templates.
Yeah. So the way that templates work, you can have a generic implementation which makes assumptions about the input types. So say you have template with class A and class B, you can the way that templates work in C++ is if you haven't seen that exact set of types in a template, it literally kind of string pastes a new function which has a linker symbol, which is some concatenation of the template name and the types, and generates code. And either that code generates because the types that you use have all of the expected methods and behaviors, or it doesn't. And so that is sort of the generic thing you can do. So if every type has some method, then no, you don't need to specialize it for strings. But if you want to take advantage of some special behavior, or you want to convert through strings some specific way, then yes, you do have kind of these specializations in templates. And so old MemSQL CodeGen did take advantage of specialization. Do we end at 120 or 130? Okay. No. So there's an old rule in compilers. You can kind of pick two of these three things: fast execution time, fast compile time, and fast development time. So here's some examples, and I'll survey the class. So if you think about assembly, what are the two that you get?
1 and 2.
Yeah, so well-written assembly is definitely fast, and there's no compilation, right? Or minimal kind of, maybe you convert text assembly to bytecode. But who wants to write code in assembly? C++ is fast execution time and fast development time, but really slow compile time. I mean, really slow. Instantiating a template costs like 50 milliseconds in the compiler. And Python, again, fast development time, fast compile time and fast development time, but slow execution time. JIT compilers kind of turn this on its head. So what a JIT lets you do is develop something quickly and compile it quickly, generate code that executes slowly, but over time, identify the pieces of code that need to be compiled and actually do it in the background, compile them to be faster and faster and faster. So JIT compilation, it's kind of like a plan cache, lets you start with one extreme trade-off and quickly converge to the appropriate trade-off for a workload. And so here's a layout of how code generation looks like in MemSQL. So we'll walk through the old code generation first. So you start with SQL text, you parse it, you generate an abstract syntax tree, you optimize it, you have an optimized relational tree, you plan it, then you have an execution plan. So a system like Postgres stops right here. And you can actually, anything that's this parallelogram is executable. Now, MemSQL would take this execution plan and run through C++ CodeGen and convert this to C++ plan. This is usually pull-oriented, and this is push-oriented. So this conversion is not as straightforward as you'd think, but it's very, very doable. And we'd take the C++ code and run it through slow GCC and generate very, very fast machine code. So that's how it works before. Now what we do is, instead of the C++ code gen, we introduce this thing called AST builder. And it's not exactly like the printf functions that we had for C++ code gen, but it's pretty close. So it's built in a way that is very familiar for someone who writes C++ to kind of produce an AST in this high-level language called memSQL programming language. And I'll show you a snippet of it in a moment. But basically, this thing is optimized very well for us as memSQL engineers to go from a system which generated C++ to a system which generates some other programming language. And it has a number of the sort of constructs that you would expect in a programming language, like if statements, for loops, etc. It also has some memSQL-specific language constructs that make it very nice for CodeGen. We then take memSQL programming language and emit a bytecode called memSQL bytecode. And this thing can actually be executed or interpreted, and it's faster than this, but slower than this. So we could have stopped here if kind of that was our goal. But what we do, and I'll explain this in a little bit more depth, is we actually implement each of these opcodes in C++, and at server compile time, convert this C++ into LLVM bytecode. And so at query compile time, we can take memSQL bytecode, and for each opcode, we have LLVM IR, which implements the opcode, and stitch it together very, very efficiently into LLVM bitcode. So going from here to here is less than a millisecond. It's extremely fast. Sometimes if the query is very complicated, the optimizer is a little bit slower than that. But this is very, very fast to get to LLVM bitcode.
All right, so what's the 1 millisecond thing?
From SQL all the way to here, yeah.
So you're supposed to be Yahoo query, right?
Yes, yeah.
So do you need to declare the statement as a preference statement?
No,
Okay, so you automatically compile it, right?
yeah. And that's the point of a plan cache. Plan cache will tell you whether you've compiled this kind of thing before or you haven't.
So you compile for the OLTP transaction as well as the OLAP transaction?
Yeah, it's the same. There's no, if it's a stored procedure on a Tuesday, then we'll compile it. And if it's an ad hoc query on a Wednesday, then we'll interpret it. It's any query that you run, any statement, prepared, not prepared, in the middle of a transaction, ad hoc, sent by Tableau, sent over the command, it just doesn't matter. We take SQL and we go through this process every single time.
So do you invalidate plans when you have new access methods, or you basically create an index?
Of course, yeah.
Okay.
Yeah.
Do you drop everything, or you drop like a subset which are actually
Subset, yeah. What's up?
So what actually do the opcodes look like, and what
We're going to look at that in a second, yeah. And the last part is we take this LLVM bitcode and convert it to machine code. So this is still expensive. It's not cheap. LLVM is making a lot of very significant optimizations. The biggest one is making inline decisions. And there's another thing like converting infinite registers to finite registers, all that kind of stuff.
Roughly how long is that?
So it depends on the complexity of the query. What we found is that it is roughly linear with the amount of LLVM that we generate. So simple queries generate in less than 50 milliseconds. More complex queries can take 200 milliseconds, and outrageously complex queries can take like a second.
Have
Yeah.
you explored turning off a few passes and figuring out which ones to put?
Oh yeah.
Okay.
So our design goal is to make code generation as fast as we can without sacrificing query performance. Because remember, we're going from, we're a real system that real customers are using and expecting to be performant, right? So if you're Acme Corporation and you're going from memSQL version 4 to memSQL version 5, your queries cannot get slower. That's not at all an option, right? So we need to make sure that we are optimizing and generating code that runs queries as fast as before. Now, of course, we will make this faster and faster and faster over time, but our baseline is that we cannot regress execution performance. So let's look at some code. Here's that same select concat foo and var thing. Before someone bike sheds me on the time, I didn't update the time on the slide, but it's not 0.81 seconds. So I just copy pasted the one from before. Here's a snippet of MemSQL programming language code that we generate. So it looks kind of like the C++ code. You can see that there's no templates. It's actually kind of concat only operates on strings. Conversions are explicit within MPL. In this case, there's no conversions necessary because this already operates on strings. And it looks kind of similar-ish to a procedural language like C++. Now this is too small, but this just gives you an idea of how much MemSQL bytecode is generated for this precise snippet of code. And if we zoom in a little bit, this is what the bytecode looks like. So you see operators like concat, and this is a very high-level bytecode, right? So concat is an opcode which takes two variably allocated strings as arguments and populates this kind of destination variably allocated string. There's no assembly language that operates on variably allocated strings, but our bytecode is pretty high level. So one of the kind of, as a compiler implementer, you want at least one stage of the IR that you build to be the highest level kind of fully sequential bytecode-like thing that you can generate. Because going from this high-level bytecode to lower and lower and lower levels of bytecode is pretty easy. Going from a tree to bytecode is pretty hard. So you want to kind of make that task as a compiler implementer as easy as possible by having a very high-level bytecode. And if we look at the implementation of concat, it's very simple. So this is C++ code. And like I said, this at server compile time is generated into LLVM that can be stitched at query compile time. And so it's just concat operator. It returns a bool, which is success or failure. It has a deep string, which is a result. String base, which could be deep or shallow. It doesn't care. As arguments and a thread ID. And it's pretty simple C++ code. So this doesn't look unlike this C++ code that we were generating before. So I want to stress that we had kind of a few design goals with LLVM code generation. Some of them are obvious, some of them are less obvious. So the kind of obvious one is we want very fast code generation. And then you brought up a very good point. Another sort of slightly less obvious one is we are a commercial system that's in production. We expect customers to upgrade to this version of MSQL, which they are right now. We shipped about a month ago. So we cannot regress execution performance. Customers buy MemSQL because of execution performance. What's up?
An alternate architecture would be to take the integral path the first few times and then do this outside the critical path, right?
Yes.
Why did you not consider that?
We did consider it. Yeah.
Okay.
So there's a few
What are the
reasons.
cons?
There's a few reasons, right? One is it's strictly more complex to build. So it's something that we may do in the future. Or you can kind of think of it as it's strictly more general than what we have today. Another con is that the first time you execute a query, it may be slower than what a customer expects. So remember when we showed this C++ CodeGen example, even with compilation time, it was 1.37 times faster. So it requires a significant amount of research to make sure that you're only doing that for queries where the execution time difference and rather the compilation time is expensive enough that the overall execution time for a compiled query is greater than the first time you interpret code. And it actually turns out if you run a little bit of experimentation with the current implementation, for a lot of queries that's not the case. So it's not as simple as like, oh, let's just try running it 3 times and then compiling in the background. You actually need to really, really make sure you're not regressing execution performance by doing that.
And how did you go about designing the primitives in the MemSQL programming language?
So the primitives were, let me answer the last question, the last sort of non-obvious design consideration, which kind of overlaps with that question. So the last thing is that we had about 8 months to go from system in production that has C++ code gen to system in production that has this LLVM code gen. And so we wanted to make it very, very straightforward for our engineering team to go from one state to another state. And so a lot of the constructs in MemSQL programming language resemble the constructs and sort of abstractions that we used inside of our code base to generate C++ code. And so, for example, some of the things that we used heavily in C++ were things like if statements and for loops. But we didn't use do-while loops that much. So do-while loops don't exist in MPL because we never used that feature in C++. Another kind of cool thing is we instantiate templates at server compile time in MemSQL, which generate conversions from one type to another. But the tree of conversions is generated at server compile time. And in MPL is resolved as an explicit composition of function calls for conversion. So that lets us, as MemSQL engineers, reason in terms of, I want it to start at this type and end up at that type, which is kind of what templates are like. But under the hood in MPL, it actually generates an explicit set of conversions.
So one reason you went with MPL was because you wanted to avoid all of the going from C++ source code to the actual ASC, because you basically want this so that you can do some simple analysis on it and then pass it to the
I think they're compiling a lot upfront, right?
Yeah,
with MPL, you can compile a lot upfront.
So there's two reasons, yeah. So first is most of the C++-like things that we were doing, we could do at server compile time. And with MPL and the compiler built into the engine, we can actually compile away a lot of that stuff at server compile time. Now, for me, it kind of sucks because the server takes a little bit longer to compile on my laptop than it used to. But that's fine because for users, that means they're not running that stuff every time they compile a new query. The second reason is that, I guess there's three reasons. The second reason is that we weren't using all of the features in C++, and in particular, we didn't need exactly the semantics that templates give you. So templates were a large percentage of the cost in C++ code gen. And there's sort of inexplicable costs associated with compiling C++, whose semantics we don't really sort of, those things that we're paying for with C++, we don't really need from MemSQL. And the last thing is that we kind of started by trying to generate just LLVM. And then we're like, oh, we need a higher level IR on top of this. So we started by trying to do that, and then we kind of started implementing if statements and loops and stuff inside of this bytecode and said, okay, well, it actually would be nicer to have a higher level abstraction even on that, which kind of gives you these basic reusable constructs that we use. And so it's sort of the minimum viable programming language that you can efficiently write code-generated sort of code generation in. Yeah.
But you still don't completely co-generate the entire join algorithm or something, right?
We do.
These are components that go into that.
Nope. Yeah. So we take a tree, we convert it to MPL. MPL is converted to this much bytecode, and then this much bytecode is converted to this much LLVM, and we run it.
So how are you dealing with the instruction cache? Like do you have issues with the size of the code footprint?
Yeah. So I mean, we have a lot of heuristics about. So that comes down to the inlining thing, right? Inlining is one of the, if not the hardest problem for compilers. So LLVM has some great stuff. LLVM is tunable to have even better stuff. And we even further make explicit decisions about when to inline and when not to inline things. So that's another world of optimization. So there's kind of a fourth reason that this architecture makes sense, which is that the code that we generate is very much a reflection on how well MemSQL will execute. And instead of using a black box of GCC, there are a lot of places, and we have a lot of compiler expertise at MemSQL, there are a lot of places that we can more explicitly sort of tune or change how we're generating code and control how we're generating code to get much better results. So one of the sort of results in MemSQL 5, there are some architectural changes that enable this as well, but queries are also significantly faster to execute. So in a lot of cases, especially on the column store, queries are something like on average 10 times faster to execute. Yet another benefit is that it really, really enables us to generate and kind of make more and more optimizations efficiently on our code. So one of the themes in building a database that you find, especially with commercial databases, is that you bring more and more of the world into the database over time. Like more and more things that the operating system does, the database does. More and more things that the compiler does, the database does. And a lot of what databases do is sort of vacuum suck away abstractions that programmers tend to rely on and rebuild them in the assumptions of the database. What's up?
So when you're doing these ops, are you generating writing vector code for them, or these ops not vectorized?
So inline scans enable you to not have to vectorize operators, right? So there is vectorized execution over rows, but because we have inline scans, we don't need to make these operators accept batches of data.
No, I'm talking about SIMD, not.
Yeah. So LLVM can actually take the LLVM that's generated by stuff like this.
Okay.
Yeah.
You're relying on LLVM.
Well, so again, to some degree you rely on LLVM, and LLVM is not a silver bullet. So you also need to tell LLVM how to and where to do these things, right? So you can do things like, I want this chunk to be SIMDable, and give me a compiler error if it doesn't match the constraints that you need to make this SIMD. And furthermore, I want to take this thing and compile a SIMD version of it and give me an error at server compile time if you can't. So all of this stuff is very, very sort of pluggable and not, I wouldn't say easy or straightforward to do, but very, very doable.
So the way it works is for the individual operators, you have your programmers write the actual implementation of those operators in a MemSQL programming language, and you compile it at like server time, like when it's actually compiled.
No, operators are implemented in C++.
Oh, the operators are implemented.
Yes.
Okay, so does anyone actually write the MemSQL programming language, or is that just an intermediate thing?
So no one writes text MemSQL programming language. People write a C++ domain-specific language, which generates an abstract syntax tree that can be pre-printed to MemSQL programming language.
Okay.
So you write kind of like a fancy type-safe MemSQL programming language, which can actually do a lot of sort of type verification and things like syntax errors. We don't need to waste any time checking for syntax errors at query compile time, but that does incur a cost in C++ code gen, or binding errors. Like we know that every variable is bound by the time that it's used. We know in a lot of cases we can do type inference at compile time rather than at runtime. And like I said, that makes the server compile a little bit slower, but it's worth it. We're actually doing some interesting work on that front as well, which I can talk about afterwards.